Hi, in today's video, we are going to discuss about some filter types. Let's start with a very common filter type called COM filters. COM filters, basically the magnitude plot looks like a comb. So it has basically multiple pass bands. Okay, so just to show you a figure, this is the magnitude response of a COM filter. You can see uh, if this is single spike, then this will have multiple spikes. So this is a low pass filter. It allows low frequencies to pass and cuts off the higher frequencies. But the COM filter, this is a COM filter which has got uh, multiple pass bands. It allows frequencies close to zero, but also in other regions. It looks like a comb, right? So that's why it's called a comb filter. Okay, so let's come to the general formulation. So GZ, this is the comb filter. This is equal to HZ to the power L. So basically you have, you know that this is a repeating h e to the power j omega repeats over omega. So this is like a compressed version. You have compressed the omega axis by some factor capital L. So this is what it becomes. Now a question can be asked, what is the value of L here? So see, so to compute that, you see what is this? Omega. So if this is 1, this is pi basically, omega upon pi is plotted here. So this is pi, then okay, 1, 2, 3, 4, 5, 6. So this is 6 times this, so this is 1 upon 6, right? So, and this is 2 upon 6, 3 upon 6, 4 upon 6, 5 upon 6, 6 upon 6, which is 1. So this is 1 upon 6. And what is this? It is 1 here. So 1 becomes 1 upon 6. So there's a scaling factor of 6. So L is equal to 6 here, right? Okay, I hope this is clear, that you have H and you're compressing it by a factor capital L. Okay, now given Hn, how does Gn look like? So we saw in the frequency domain, given h e to the power j omega magnitude plot, how does g e to the power j omega looks like? But now the question is, given Hn in the time domain, uh, what is the form of Gn? So we have to do some manipulation. Okay, what do we know? I just know that my Gz is equal to h z to the power L. This is the only thing I know. Now, can we derive in terms of Gn? Okay, let's start with maybe the left hand side. So my Gz is equal to uh, summation Gn z to the power minus n and summation over all n basically, right? Um, Now on the other hand, my h z is equal to summation hn e to the power, sorry, z to the power z to the power minus n. So now let us see what is h z to the power l. So this becomes simply nl and summation over all n. So what do I need here? I need a factor n here. So let us replace. Uh, so I put, so let me keep this notation as m because it's a dummy variable. Put m equal to n times l, right? Then the z term will match. Then this becomes summation over n because m goes from minus infinity to plus infinity. So this limits don't matter here. G of nl z to the power minus nl. Now if you compare the two terms, so you know the left hand side and right hand side, they are equal. If I compare them, then what do I get? That this term and this term, they should also be same. So basically I get g of n is equal to h of n upon capital L. And you know that your L is an integer and your small n, uh, means this value will be 0 if n upon l is not an integer, and this will be non-zero only when it is an integer. So okay, let us plot. How does it look like? So if my h of n is this, if my h of n is something like this, okay, so this is my h of n, so 0 1 2, and this is n. Now my g of n will be something like this. So g of n, when n is 0, it is equal to h of 0. So same, no problem. At 0, no problem. Now when g of 1, it's h of 1 upon l, which is a fractional number. So this will stay 0, 0 until n upon l becomes 1. Then it will be equal to h1. So at some l, this will become 1. This is basically h of 1, right? And similarly for 2, this should be equal to 2l. So again at 2l, it becomes h of 2. Here it is h of 0. Okay, so in this way, so what we have seen is in between there are many zeros introduced. So that is the whole idea. In the time domain, it's like like in the omega domain, you are compressing the axis, and in time domain, you are stretching the axis by introducing zeros in between. Okay, now so this is the formula: g of n is equal to h of n upon capital L. Now the question is, how do we implement this filter? Let us say so first let us see how do we implement h of z. So basically, what is the meaning of implementation? That you have, this is an LCCDE, right? So you have some input x of n, and you have the filter h of z, or you can say it's h of n, and you have an output y of n. So let me write it in terms of yn and xn. So this is equal to yz upon xz, right? So now if I multiply, so xz times b naught, and if I transform to the time domain also, so it becomes b naught x what xn plus b1 xn minus 1, I'm sorry, b1 x of n minus 1, this is equal to y of n plus a1 times y of n minus 1 plus a2 times y of n minus 2. Okay, so what is yn then? My yn is simply b naught times xn plus b1 times xn minus 1 plus, sorry, minus a1 times yn minus 1 minus a2 times y of n minus 2, right? Simple algebra. Now, how do I implement my h of n? So basically, I have some x of n coming in here, and so now my y of n is, let's say it's here, my y of n is b naught times x of n. So let me have a multiplier. It multiplies with factor b naught, right? Plus b1 times xn minus 1. Okay, so I have to generate xn minus 1. How? By introducing a delay term, z minus 1, right? One time delay, so that this is xn minus 1. So we have b1 times, so again a multiplier, b1 times xn minus 1, and they get added. So I put an adder here, and I add the two, right? Now This is a1 times, so minus a1 times yn minus 1. Okay, so I have to get yn minus 1, no problem. So I will put a delay here. I have a delay here, and this output goes to another multiplier, which is minus a1. So this multiplier is minus a1, and it gets added here. And then again, another delay to get yn minus 2, and this output again gets multiplied with minus a2, and the output gets added here. So this is my implementation of hn. So this is hn. In this way, so this will give me the output is filtered through hz. Now how do I get g? Okay, so now I want to get, this is gz or gn, right? So how do I get that? So gz is simply equal to this is equal to h of z to the power l, or my g of n is equal to h of n upon l. Okay, uh, if I go with the formula of let's say simply my gz is h z to the power l, which means here I get z to the power minus l, z to the power minus l, z to the power minus 2l, right? This is my gz, right? So if I have to get a gz, then I have to just replace them with l. So what does that mean? Here it will become n minus l, here it becomes n minus l, here it becomes n minus 2l, right? And similarly here. So what do I basically get? My delay is l times more. So this becomes z to the power minus l, z to the power minus l, z to the power minus l. So all my delays, so basically I replace my delay function or delay block by z minus l, this delay block. So I increase the delay l times, I mean by l time indices. Okay, so this is all about COM filter, and in the next discussion we'll discuss another kind of filter which is called an all pass filter. Thank you very much.